All right, let's go to page 44. We are interpreting derivatives in context. So we know how to find derivatives. We have to make sure that we understand what the heck they mean. All right, so here's the graph of f of x, along with the line that is tangent to f through the point 1, 0. It is known that f prime of 1 equals 3. Even if they didn't tell us that, could we figure that out? Yes, because we can see the slope of that blue line, right? All right, so if we want to interpret the meaning of the statement f prime of 1 equals 3, okay? So if we know that f prime of 1 equals 3, what does that tell us about, what does that tell us just in general? What does f prime tell us just in general? The slope. F prime tells us how f is changing in terms of the slope, right? So f tells us how f prime is changing, and it's telling us, since it's f prime of 1, how it's changing exactly at 1, right? Because it's different when it's changing at different x values, right? And how is f prime changing? At a rate of what? 3. Okay. So if we are talking about how something is changing at a given point, that is the rate of change, that is our slope. It's changing at an instant, so that is our instantaneous rate of change. Okay? So the instantaneous rate of change of what? F is what? 3 at what? X equals 1. Okay. So when we're talking about the instantaneous rate of change, how the function is changing at a specific point, we have to make sure we say at what, and it has to be at an X value. Okay. And of course, if we had more information here, we'd have units and stuff like that to go through. Okay. And that's what we're going to look at is when they're actual application problems, how do we just interpret what's happening? How can we find what's happening? So we've been studying derivatives, including our differentiation rules, the meaning of the derivative graphically. However, problems we've been working with have been without context. That's what we've done so far. Now we will see examples of functions that have context, meaning they're actual application problems. We actually see what we're looking for here. When functions have real-world context, then the derivative will also take on real-world context, right? It'll make more sense what the derivative actually means. Okay, so a couple of important notes here. Number one, in real-world context, we rarely use x and y for variables because those are just our generic ones, right? Instead, we use variables that correspond with the situation. We often use t for the horizontal axis because a lot of times it's time. So it makes the most sense, okay? In contextual problems, derivatives have these units of y over units of x. You don't even have to make sense of it. You just literally put whatever the units of y are over whatever the units of x are, and don't worry about trying to overthink it. Okay? Sometimes it won't even make sense to you. It's totally okay. Third note, in real-world context, a derivative is a rate, and rate is slope, right? So we're talking about, so instead of saying it's the slope, which it is, we'll talk about it as the rate. It is the rate of which something is happening. Derivatives are still instantaneous. They occur at an instant at like a t equals 3 minutes, okay? So here are some things derivatives are, what it means, and what it doesn't mean. So derivatives are rates. So we say the rate of blah, blah, blah. They're not totals, amounts, or averages. Okay, it is a rate of something. They are instantaneous at t equals. It's not over intervals of time. We've been talking about things over intervals of time. Now we were talking about instantaneous. It's happening at a specific point of time, not over an interval. They're contextual with units of y over units of x, and not the units of the original function, okay? Even if you might think that it's supposed to be that way. All right, we all good so far? Okay, so let's see. The height of the sunflower in inches is measured over a course of 7 weeks we're going to use the table above to estimate. Okay, so here's a couple of important things. We're estimating this. We're not going to be able to actually find exactly what it is based on what we have, right? Okay, y'all going to let me in on the joke? Those tables are laughing. And if you're laughing at me, you have to tell me because I want to laugh too. I know y'all can be laughing at different things. Y'all are just giggly today. It's okay to be giggly. It's okay to be giggly. It's very sunny outside. Maybe I need some vitamin D. You're just being silly. Okay, so if I want to estimate h prime of 2, I have h. I want to estimate h prime. So h prime is going to tell me how h is changing, right? So I can find that. 2 goes right here, right? 2 would be in between 1 and 3. So I can estimate it using that interval, okay? So if I want to find the change, how it's changing, that is a rate, which comes from slope, right? So I can do the average rate of change from 1 to 3. Does that make sense to you? And it's just straight up slope. So here's a couple of things about notation that's very important here. This is h prime of 2 that we are estimating, right? So we're going to say h prime of 2 is approximately, we got to put the squiggly equal signs, okay? Squiggly is important because it means it's about, okay? Because we can't say exactly what it is. We're approximating. So then we are going to find h of 3 minus h of 1 over 3 minus 1, okay? One of the things that they look for when they're scoring this is, did you actually show a difference, okay, which is a difference quotient. We're subtracting, you're actually showing some work here. So then h of 3 is 25 minus h of 1, which is 7, over 3 minus 1, which is 2. So 25 minus 7 is 18. So I get 18 over 2. Which is 9, and then we want to put units on it, right? The units of y, which were inches, over the units of x, which was weeks, inches per week. Okay? You can write out the words inches per week if you want to, but you can also just do that. We all good so far? Okay, so all it said was to find it. That's what we did. Now, notice my little squigglies here. No squigglies here, no squigglies here, because this is approximately this, but this is exactly this, which is exactly this, which is exactly this. Does that make sense? So the squigglies only go once. Okay, we good? Okay, so we're not interpreting that yet, we're just finding it. Okay, so in example 2, the number of cars that enter the parking lot of a grocery store t hours after it opens is changing at a rate modeled by the function c prime of t, where c prime of t is measured in cars per hour, and it does tell me that right there. Use the table above to, again, approximate c double prime of 6. So c double prime is going to be how c prime is changing. So c double prime of 6. Can we find that exactly? Or are we approximating? We're approximating. So squiggly. 6 fits in right here. So I'm going to find between these two, right? Using between 5 and 7 is way more accurate than between 0 and 7, right? And so this is going to be c prime of 7 minus c prime of 5 over 7 minus 5. Then that's going to give me 54 minus 92 over 2. 54 minus 92 is negative something, right? Negative what? 40. What did you say? 38? Is that what y'all got? Over 2. Am I right? I think I'm right. Yeah, I was right. Over 2, and then that gives me a negative 19. And then my units, cars per hour over hours. It's cars per hour or cars per hour squared. Okay? Again, The units don't have to make any sense to you. Just write them down. Okay? Things might make a little bit more sense after we talk about some other things, but sometimes they may not make sense to you at all. It doesn't matter. Just write it down. Okay? Do the hours cancel out? They absolutely do not. Okay? So don't go doing that stuff. Don't try to fix it. Just, that's it. Okay? We good? It's like distance, velocity, acceleration if you were in physics. So. Okay, so now if we're going to interpret the derivative in context, okay? Context, don't just name the function, include what the function is modeling with words. So I'm not going to call it just f anymore. I wouldn't just call it c prime. I need to talk about what c prime is, right? Units include the units for both the answer and the x variable. So we said like at x equals 1, it's going to most of the time be at x equals 1 minute or t equals 1 minute or whatever happens to be. Instantaneous time must be clear at t equals, or don't have an interval of time, right? And include the word rate in your sentence. All right, so we are going to interpret the meaning of example 1 from above. So it says the blank. So we are going all the way back up here, f of t in context. So what is f, or what, this is actually h. What are we actually talking about here? The height of what? Sunflower. Okay, so we're going to say the height of the sunflower, height of sunflower, leaving out the, it's okay. There's not really a lot of room for that. Okay, is the height increasing or decreasing? Increasing, and how do you know? Because it's positive, right? What's happening to the rate in example 2? Is it increasing or decreasing? Decreasing, because it's negative, right? Okay, so I know that it's increasing because it's positive. So it is increasing at a rate of, okay, notice it says the absolute value of f prime of c, because if we were talking about example 2, I would say it's decreasing at a rate of 19 cars per hour per hour. I wouldn't say it's decreasing at a rate of negative 19. Does that make sense? The increasing or decreasing gives you your positive and negative. All right, but that's not the one we're on. We're on this one. 9 inches per week at t equals what? What was it? 2 weeks. Now, this, because of this actual question, this that's written out is actually missing something. Okay, and before I copied it, I wasn't confident enough to put it in there, but because when it comes from certain people, you're like, there's no way any of this is wrong. But the height of the sunflower is increasing at this should be, instead of should it be at an approximate rate, because it was an approximate rate, right? So it's increasing at an approximate rate of 9 inches per week, right? Because we didn't know what it was actually right then. Okay. We good so far? When it's not approximate is when you're going to be able to find it exactly, like if it's a calculator problem or if you had more information. We all good? All right. Yes. Yeah, that would too. A graph would be good too. All right, so this is I guess I need to give you the next piece of paper. Like, turn it over again, and it should magically change. There you go. All right, so now we are going to, so what page is this one then? 45, thank you. And there's barely any room there, you know. Okay, so now we're going to not only approximate it, but then also give the answer in the context of the problem, which is more like what you're actually going to be asked to do for these. So a factory produces delicious cans of corn, not just cans of corn, but delicious cans of corn for the typical corn enthusiast. One particular machine is notorious for packaging cans of corn at impressive speed. The amount of cans this machine has packaged after t seconds is modeled by the differentiable function c of t. Okay, so let me ask you this. If it is differentiable, what else do we know about it? It's continuous. Okay? So that way, if we had to, which we don't on this particular question, but there are some questions when you answer them, you have to say c of t is continuous, and so you would have to say something like, since c of t is differentiable, it is also continuous, and then blah, 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 right? We don't have to say that for this one, but those are words that you need to make sure that you have connected for when you do need to say that. Okay, so we need to find c prime of 1. So I think the interval from 0 to 2 would make the most sense, yes? So c prime of 1 is approximately, so squiggly, equal signs. We're going to do c of 2 minus c of 0 over 2 minus 0. C of 2 is 52 minus 16 over 2. So 52 minus 10 is 42. Then I subtract 6 and get 36. 36 over 2, and that's 18. What are my units here? Cans per second. Very good. Okay. So I found it, and then it says, using correct units, interpret the meaning of this value in the context of the problem. So you have that other piece of paper if you want to look at it, how we start. So we can say v, okay, so c prime of t is how c is changing, and c is what? Number of cans, okay? So the number of cans packaged is it increasing or decreasing? Increasing, increasing. At an approximate, right? Approximate rate of what? 18 cans per second. Cans per second at t equals what? 1 second. Okay. We good on that? What questions you got? All right, so the next one is one that we can do on the calculator. Do y'all have your calculators? So we want to make sure we add a calculator and then also add a graph. All right, are we all okay on how to do that? Okay, yeah, control doc, which is the plus page part there. All right. Now, what we want is, we have this function here. This is not something that we want to take the derivative of by hand, right? So we want the calculator to do that for us. Even though we don't really care at this point what the graph looks like, we are actually going to graph this. So let's, when we want to get we want it in a fraction, how do I make sure I can start typing in a fraction? Control division symbol, yes. Okay, it pops up like that. So we're going to type in 50,000. And then in the denominator, I'm going to have 1 plus 535. And then e to the x is right here on the row with 1. And then that's going to be negative 0.29. And you can't use t, you have to use x. Okay? It should look like that. Let me know if you are struggling with any of this at all. I know we haven't been using it that much. Then how do I get my graph to actually pop up? Enter. And I can't really see it. Don't really care right now, okay? There are times where we're going to need to do stuff off the graph, but I don't necessarily need to see it right now. I just need the calculator to know what the graph is for me. So then I also need the derivative. I'm going to also graph the derivative. Now that I have graphed it, am I going too fast for anybody? Speak now if I need to slow down. Okay, how do I get back so I can put in another graph? Tab. It's the one that's kind of weird, right? So now I have f of 2 in my cursor's in the way. Okay, so I have f of 2. I want the derivative in here. Do you remember how to find the derivative without doing any work, really? It's this button. I can't even see it on here. I think it's the book. It looks weird on here. I have to look at an actual calculator. Sorry. Mine's all just blurry. Nope, that's not it. Ugh. Yeah, it's the one next to 9. It's one next to the book, sorry. Those are all blurry. It's hard for me to tell what's what. It's the one right next to 9. It's this thing right here. So I'm going to push that button. And I want the D blank, right? Mine's already highlighted because it's the only thing I've used on there. But you find it. I know it's tiny. So we click that. And you have to put in that you are taking the derivative with respect to x. Put in my x there. And what do I want to take the derivative of? f1, right? So I can just type in f1 of x. Okay, yeah, you have to put the of x in there. Everybody okay with that? Tell me if you're having issues. Are we good? So I'll hit enter, and I can see part of the graph too, but again, what the graph actually looks like for me right now is not important. Again, sometimes we need the actual graph. Don't really need that. That's most likely what y'all can see as well. Okay? Are we all good so far? You're not even doing anything. What are you doing? Spider-Man? Really? Where's your calculator? Get up and go get a calculator and do this. I'm so disappointed in you. Okay. Goodness. All right. Now, I'm not going to wait on Daniel to catch up, but I need to wait on anybody else. It's okay. Because if you hit one wrong thing, sometimes you got to start over, and it's frustrating, I know. Are we good? Okay. So now what I want, what am I looking for? I'm looking for f prime of 8, right? So the calculator can just do that for me now that I've typed all that stuff in. So, but I need to go to my calculator part. So how do I get back to the other page? Control left, right? And then I just want, where's f prime? In the graph, in which graph? f2, right? So all I need to do is evaluate f2. f2 of what? 8. So notice I'm not actually taking a derivative here. I already took the derivative. I have the derivative as a function, right? And I'm evaluating f2 at 8, and it gives me this number. Okay? It's the easiest way to let the calculator do this stuff for you. So we have 265.5901. So I'm going to write over here f prime, capital F prime, right, of 8 equals 265.5901. You have to be correct to 3 decimal places, so if you just write 4 of them down, you should be, you don't have to worry about rounding or anything, okay? All right. Any questions on how to get that? Okay. So now we have to explain our answer. So we found it. then we have to use correct units and interpret the meaning of this value in context with the problem. Actually, what are the units on f prime of 8? Yeah. It's the number of, so fans per minute, right? We can do fans per minute, or people per minute. That's what can get on there, right? That's our units. Now when we go to say what's happening here, right? F prime is describing how F is changing. What does F represent? Fans what? Exiting the stadium. Okay, so fans are exiting. Oh, wait. Yeah, number of fans, right? Yeah, shoot, sorry. Well, I'm going to erase. You can just edit in there if you want. It can't just be fans. It has to be number of fans. That would make more sense. Number of fans exiting. What are we exiting? The stadium. Increasing or decreasing? Increasing. Number of fans exiting the stadium is increasing. Is this an approximate rate? No, it's an exact rate because we found the exact derivative, right? So we don't have to put approximate there. Number of fans exiting the stadium is increasing at a rate of 265.5901 fans per minute at t equals what? 8 minutes. So this first part of this right here, which I struggle with sometimes too, you may not have worded that part that I underlined in green exactly like I did if you were to answer this question on your own. And sometimes when you start to word it, then you realize if you write the rest of the sentence, what you're writing isn't making sense. That's what just happened to me. It is fans exiting the stadium, but it's the number of fans. It's not the rate at which or anything. It's the number of fans. Okay? What questions you got? We good? Need some help there, Daniel? All right, anybody else? If you have any calculator issues, you just got to speak up. I'm willing to slow down or help you with something. You just got to speak up. Okay. But you have to do it. Okay. All right, so let's look at example 6. For t being between 0 and 10, which is what our graph is, the rate that people are getting on an escalator in people per second is modeled by function p, where t is measured in seconds. I highly suggest that when you're given something like this, that you actually label your graph. So it says the rate that people are getting on the elevator in people per second. So this right here, my y, this is people per second. And t, this right here, is measured in seconds. Okay, so that you don't mess up on your units. Because sometimes you get 1 point just for having your units right. So if all else fails, write down what the units are for the answer. All right, so we're going to use the graph. I'm serious. We're going to find, so this is p. We want to find p prime of 8. Okay? So p prime of 8, here is 8 right here. What is p prime of 8? -1/2, right? Because it would be the slope, right? And this is a -1/2. Okay? And it's -1/2. My units are people per second per second. It's the rate in which the rate is changing, right? And again, don't let that mess with your mind too much. Just write it down. Okay, because we have a rate, and when your rate changes, that's like your acceleration, right? Okay, so using correct units, we're going to say, so the rate so p prime is the rate at which P is changing. P is the rate at the people are getting on an escalator. Okay, so the rate that people are getting on an escalator okay, that's a lot of words, I know, but it is what it is. Is it getting on an escalator? You know what I mean. It's okay. This is not English class. We're fine. The rate at which people are getting on an escalator, is it increasing or decreasing? Decreasing. Is decreasing is this an approximate rate? No, it's an exact rate because we got it from the graph, right? Decreasing at a rate of, is it 1/2 or negative 1/2? 1/2, because the decreasing took care of the negative. 1/2 people per second at t equals 8 seconds. Okay. Do you understand how to pull all that out of the question? And if you're just methodical about it, you do it in the same order each time, you'll be fine. Okay? Are we all good? Awesome.